Simplified dynamic method applied to the study of slope stability. Mamba Mpele. Abstract. The stability studies of slopes by the classical methods based on the concept of safety coefficient present some insufficiencies. They do not allow the calculation of permanent displacements induced by earthquake. To overcome this limitation, finite elements, or finite volumes methods have been developed and introduced in several civil engineering calculation software. But, because the implementation of above methods is complicated, they cannot be used as a design tools but rather as a verification tool. In this paper we shows that simplified dynamic methods for the study of slope stability under dynamic loads have been developed in the literature and their implementation is very easy, and allow the calculation of irreversible permanent displacements induced by an earthquake, which can be used as a design criterion for slopes or embankments stability. Keywords: embankments, stability, simplified dynamic method, earthquake. 1. Introduction. A stability study of slopes or embankments, whether natural or artificial, consists of 2 steps. The first one concerned to geotechnical studies which permits to calculate the mechanical and physical characteristics of the soils constituting the slopes or embankments and its base. The second one is devoted to the analysis of the stability of the embankment or slope, in order to evaluate their probability of failure. This stability analysis can be performed by 2 methods, one probabilistic and the other determinist. The probabilistic approach is based on the spatial uncertainties of the mechanical and physical properties of soils, which result in an uncertainty on the representativeness of the calculation results. The implementation of this approach is very difficult and it is understandable why it is not often used by civil engineers. On the other hand, the deterministic approach, energy methods, static and pseudostatic methods, is, with a few exceptions, systematically used. The success of this approach is explained by the fact that its implementation is based on simple theories and the obtained results are easy to interpret. However, these methods have some limitations, especially when the slopes are subjected to dynamic loads. In this article, we will briefly review the static and pseudostatic methods of slope stability analysis, highlight some of their shortcomings and show how some of them have been overcome in the case of seismic loading. 2. Deterministic approach. The deterministic approach to slope stability analysis is based on 3 methods. Energetic methods, static and pseudostatic methods, dynamic methods. 2.1 Energetic methods. 2.2 Static and pseudostatic methods. 2.2.1 Concept of safety coefficient. The objective of the energetic methods is to find the most general analytical form that can be given to the normal stress function Sn. To do this, it is assumed that there is a potential function of the failure curve and that, among all the stress distributions which verify the equations of statics, the one that makes the potential minimum is chosen. This energetic approach developed by 15 is not used by engineers. Instead, they prefer static and pseudostatic methods based on failure calculations and the concept of the safety coefficient. The safety coefficient associated with a failure surface can be defined as the ratio between 1. The maximum mobilizable tangential stress max and the mobilized tangential stress T on a failure surface. 2. The resisting forces and the driving forces on a failure surface. 3. The resisting and driving moments of the above forces on a failure surface. In general, the expression of Tmax is given by the failure criterion of Mohr-Coulomb, equation 1. On the other hand, some authors, such as 15, have proposed for non-coherent materials a failure criterion given by the relation 2. The expression of the effectively mobilized stress T is obtained by solving the equilibrium equations of the mass located above the failure line or surface. 1. Max Don equals plus 2. Max 0 Bnref AP equals A 0 ETB equals 1 are positives coefficients, the reference pressure, C and F are cohesion and friction angle of soil. Rev. The equation of the equilibrium problem of a massif is based on the following assumptions. The soil mass is assumed to be continuous. The studied problem is plane and there are no edge effects. The external forces are the weight of the soil, the surcharges, and possibly the seismic forces. No account is taken of the driving forces that can be created by water flows. If there is water flow, it is not disturbed by the slope's failure and the Tiertz-Sagys relation is verified, U equals. The mass of the moving soil, above the line or surface failure, is assumed to be rigid and the equilibrium of this mass resting on the rest of the soil is studied. The seismic forces are taken into account, pseudostatic approach, by introducing the vertical kV and horizontal kh acceleration coefficients at the gravity center of the moving mass. The safety coefficient is assumed to be constant over the entire rupture area, 2.3. Slice methods. Based on these assumptions, the solution of the mechanical equilibrium equations can be done using global methods or slice methods. The principle of the slice method, figure 1, is that the moving soil mass is broken down into several small elements or slices. The individual equilibrium of each slice is studied. 3. The force tensor on the unstable mass is equal to the sum of the forces applied to each slice. By taking the definition of the safety coefficient, D2, given by equation 17, and introducing the expressions 7, 16, of N, we obtain another expression of the safety coefficient Fd, which is given by relation 18. It maxi. In the literature, there are other assumptions on the variations of 6, high and zi which have given rise to other methods of calculating the safety coefficient, 2-4-6-8-12-21. 2.4 Global methods. Figure 2, global method, mass of equilibrium. The moving mass above the failure surface, C, is considered to be a rigid block and its equilibrium is studied. The equilibrium of a small element of the rigid block of center m and length ds is. For the equilibrium of forces. To calculate the integrals of the system of equations, 28, the rigid block is subdivided into several slices in order to use classical numerical integration methods. The fundamental assumption of the perturbation methods is to admit that the normal stress distribution is a function of the vertical stress applied on the horizontal facet, the parameters, and the angle that the tangent facet to the failure line does with the horizontal axis, where the normal stress is applied. This hypothesis yields system of three equations with three unknowns that gave rise to the perturbation methods 1, 2, and 3 presented by 5 to 14. 2.5 Shortcomings of static and pseudostatic methods. The shortcomings of the static and pseudostatic methods may be found in assumptions 2, 4, and 6. Assumption 2 assumes that the slope stability problem is planar and that there are no edge effects would be partly true if the length perpendicular to the cross-section of the slope is sufficiently large compared to its width. But the dimensions of the slope being finite, it can happen that for some constructions this ratio is close to 1, bridge pairs, in which case the third dimension must be taken into account. This shortcoming led to the development of 3D stability methods by January 11, 22. Hypothesis 4 states that shear does not cause change in pore pressures at the failure surface. This statement, which is contradicted by the work of 19, has led to the development of slope stability methods that take into account pore pressure variations during shear. Hypothesis 6, which characterizes pseudostatic methods, attempts to take into account the effect of earthquakes by introducing seismic acceleration coefficients. This method is not applicable for the analysis of soil masses with a risk of liquefaction, and its major problems are the choice of seismic coefficients, which seems arbitrary, although some authors such as 7 to 18 have proposed their maximum values as a function of magnitude, focal distance, and soil type. From a theoretical point of view, this method is not satisfactory because the dynamic nature of the seismic action is not taken into account, the eigenperiods of the slope are not known, and the induced permanent displacements are not calculated, although they are used as a second, the first being stress-based, stability study criterion in most engineering problems. In the end, all the methods mentioned above have been established on the principle of limit state of resistance calculation. The fact of having a safety coefficient lower than 1 must therefore be interpreted as the resistant forces being exceeded by driving forces, criterion of not exceeding the constraints violated. The second criterion for not exceeding a threshold displacement value is also important in the dynamic design of geostructures, dams and embankments, with elastoplastic behavior, due to the existence of induced permanent displacements. For embankments, simplified dynamic methods developed by 10 to 13 were often used in the literature for the verification and dynamic pre-design of embankments or dams. Dynamic embankment design tools based on these methods have been developed by March 9, 20. In the following pages, basics of this method will be presented here. 3 Simplified dynamic methods. 3.1 Principle. Figure 3, infinitely long embankment under seismic loading. The principle of the simplified dynamic methods is based on the analysis of the elastic response of a homogeneous triangular or trapezoidal embankment of height h, based on a rigid foundation subjected to the action of the seismic acceleration, t. At the end of this analysis, the natural frequencies, the maximum distortion max of the embankment as well as the maximum accelerations, Kmax applied at the crest of the embankment and on the unstable part of the embankment, P, above the failure surface, C, are calculated. NW. The critical acceleration Kc associated with the failure surface, C, is then compared to the maximum average acceleration Kmax applied, figure 3, to the unstable part, P. If, equals 1 the unstable part, P, of the embankment, figure 3, does not move, or is stable. If 1 he unstable part, P, of the dam, figure 3, moves along the failure surface. This displacement must be estimated in order to compare it to the values of the admissible displacements tolerated by the project owner. The knowledge of these parameters requires that a study of the elastic response of an embankment under dynamic loading be carried out. 3.2 Elastic response of an embankment under dynamic loading. The study of the elastic response of an embankment, figure 4, under dynamic loading by September 10, 13 is based on the following 4 assumptions. 1. The material of the embankment body is homogeneous and its mechanical behavior is governed by a linear elastic law. 2. The influence of stored water is negligible, no significant loss of strength in relation to the generation of pore pressures. 3. The embankment is infinitely long and modeled by an infinite number of thin horizontal slices interconnected by an elastic spring system. 4. The mechanical problem considered is the planar type, where N R, density, shear modulus, and lame coefficient of the embankment material. Vertical and horizontal displacement of point M, figure 4, under the effect of the earthquake, equation, 29, after adding the second member gives the system of equation, 30. Seismic stress is a pure shear wave, figure 5. This means that A equals 0. Figure 5, principle of calculation of the acceleration applied to the part, P. The acceleration applied at any point of the unstable part, P, of the embankment located above the failure line and assumed to be rigid is 0. P. If W is the weight of the unstable part, P, which has been divided into n slices. If dm is the elementary mass of the slice I located at the coast y. The average acceleration applied on the part, P, of the embankment is 46, 10 mit W equals 47, maximum. Max 0 10 unit mit HWHU equals. And its integral form is given by the expression, 48. 48, maximum. Max 0 10 unit mi HWHU, equals. The maximum average acceleration coefficient. Applied to the gravity center, stiffness assumption, of the unstable part, P, of the embankment is 49, max stage, equals. In all that follows we assume ET, 50, .cc/kkg equals. Max .kkg equals. Max .yug equals. Based on the study of the elastic response of embankments under seismic loading, simplified dynamic methods have been developed by several authors October 13, 16. In this article we will only present the McDissey and Seeds method. For McDissey and Seeds method. Figure 6, solicitation according to 10. In the McDissey and Seeds method, it is assumed that the seismic loading is a pure shear wave. The solutions sought are those obtained previously provided that A equals 0. Let B 51, 0 gut, 0 ut, 0 max, 0 ans, 52, 200 max 100 nan us equals. 53, 200 max 21 nans hsv, equals. 54, 000. And SWS equals. 00 VNNS max VT equals. 55, 00000 X psinten VT ut, equals dash. 56, 10232.40485.52018.653 NN get wage, equals. 4.1 McDissey seed approximations. An observation by 29, of the evolution of the functions, as a function of allowed. 1. To neglect the contribution of modes greater than 3, for the calculation of the maximum peak acceleration. 2. To neglect the contribution of modes greater than 1, for the calculation of the maximum distortion max 0. 3. Consider that the equivalent cyclic distortion CYCL, is equal to 0.65 times the value of the mean distortion and that 1, 0, 0,3. 4. Consider that the dynamic shear modulus and the damping of the embankment material are functions of the cyclic distortion. A result of these approximations, we deduce the following relationships. 57, 0,5320 max 100 IAIIUUS equals 58, 59, 0 max 12.1 as HSV, equals max 120, 650, 65.1 exclamation HSV, equals 60, 120, 195. Clause HSV equals 61, 0,5222 max 1231, 6.1, 06.0, 86. AAA USSS equals plus 12101, 601, 0600, 86 equals. Using the 23 hypothesis based on the mechanical rigid plastic behavior of the soil and on the basis of the results of cyclic laboratory tests 10, calculated for different accelerations, the permanent displacements induced by earthquakes of magnitude 6,5, 7,5, 8.25 and the whole results are presented as curves representing the ratio versus figure 7, and then normalized time, 0 versus magnitude and ratio. Figure 8, which are used as charts. If D denotes the value of the permanent displacement induced along the failure surface, the variables, 0, represent respectively, the maximum acceleration at the embankment crest, the critical acceleration, the acceleration of gravity, the first mode period of the embankment, the height of the embankment and the maximum average acceleration applied on its unstable part. The ratios are unit-less numbers and D is in meters when G is m, 0 in second and unit-less coefficient for the maximum acceleration of the unstable part of the embankment. Figures 7 and 8 show the charts of 19 and with a minimum correlation coefficient of 99%. 19 proposed the relationship 62 to 67 which can be used instead of the charts. Max U 00, 20, 40, 60, 81, 01, 00, 80, 60.40, 20 YH domain de valeurs moyennes max /Q max methods de elements finis. Figure 7, ratio of maximum accelerations to depth of sliding mass according to 10. 00, 20, 40, 60, 81, 00, 00, 0010, 010, 11, 10 max 0 density 7, 50 m equals 8, 25 m equals 6, 50 m equals. Figure 8, average values of normalized displacement as a function of magnitude and the ratio of critical to maximum acceleration of the unstable block according to 10. 62, max 21 max 1 SI 01, 07 EXP 0, 372610, 492 SI 01 YHKYFYYYUHHHH equals 63, max 22 max 1 SI 01, 08 EXP 0, 2210, 985 SI 01 YHKYFYYYUHHHH equals 64, max 24 max min 1 SI 01, 117 EXP 0, 1421, 914 SI 01 YHKYFYYYUHHHH equals 4 max 0, 10, 7 CKK. Magnitude earthquake 8.25, average values. 65, 2 max 0 max 3, 67 41, 59611, 6156, 961 CCCKKKDL and KGTKKK, equals plus. Magnitude earthquake 7.50, average values. 66, 2 max 0 max 1, 86313, 69815, 5327330, 95338 CCCKKKDL and KGTKKK, equals plus. Magnitude earthquake 6.50, average values. 67, 2 max 0 max 53341, 61010, 97857, 33983 CCCKKKDL and KGTKKK, equals plus. 4.2 Implementation of the method. The implementation of the simplified dynamic method for the dynamic calculation of embankments according to 17, requires the knowledge of 1. The physical and geometrical characteristics of the embankment. 2. The dynamic shear strength of the embankment materials. 3. The fundamental period, or frequency F0, of the embankment, symbol. 4. The value of the critical acceleration, symbol, and the mean cyclic distortion associated with the earthquake. 5. The characteristics of the earthquake. 4.2.1 Fill characteristics. The characteristics of the backfill for the use of the seed and McDissy method are, the density of the backfill, measured in situ, the maximum shear modulus of the embankment material, obtained from cyclic triaxial tests, the embankment shear modulus G, obtained from geophysical tests, and the embankment height H. These characteristics are illustrated in Figure 9. Figure 9, Characteristics of an embankment on bedrock. 4.2.2 Dynamic shear strength of the embankment. The dynamic shear strength of the embankment soil, obtained from triaxial tests, is determined not only by the evolution of the stress deviator as a function of the number of cycles, but also by the variations of the shear modulus and damping as a function of cyclic deformation or distortion. When using the Seed-McDissy method, only the variations of the normalized shear modulus and the average damping factor %, as a function of the cyclic distortion %, are used. As an indication, figures 10 and 11 given by 17, show the variations of shear modulus and damping of gravel and gravelly soils as a function of cyclic distortion. 410-3, 10-2, 10-1, 10-1, 5, 5, 5, 5, 1, 0, 0, 80, 60, 40, 20, %cyclic.g/max. Figure 10, Variation of shear modulus with distortion for gravel and gravelly soils according to 17. 410-3, 10-2, 10-1, 10-1, 5, 5, 5, 5, %cyclic 0.24201612840 damping coefficient, %. Figure 12, Eigenmodes of zone dams according to April 1989. For homogeneous embankments not resting directly on bedrock, the following relationship can be used to calculate the fundamental period 0. 74, 10112. Stoff equals. Figure 13, Calculation of the fundamental period of a homogeneous dam resting on an alluvial layer according to 17. 4.2.4 Critical acceleration Kc. The critical acceleration is obtained by pseudostatic analysis methods. It corresponds to the value of seismic acceleration for which the safety coefficient is equal to 1. And the coast, symbol, being the depth at which the failure surface intersects the face of the slope. X maxi h, p, cc kkg equals w. Figure 14, Case of any fracture surface. The critical acceleration coefficient. For a flat fracture surface, figure 15, with a static safety factor, is 75, 1 tanks F equals, where is obtained using expression 76. 76, Constans in Moyababobskelwolf plus dash equals 0 YWCC kkg equals hab. Figure 15, Case of a flat fracture surface. 4.2.5 Earthquake characteristics. The earthquake characteristics are the accelerogram, figure 19, at the base of the embankment. The acceleration response spectrum, equals, associated with the earthquake, which is a function of the damping of the embankment material and the period t. This acceleration spectrum is often used in a standard Cartesian representation, figures 16 and 18, trilogarithmic, figure 17, or logarithmic, figure 20. The spectral acceleration is used to calculate the maximum cyclic distortion. Equation 58, the maximum peak acceleration, relation 57, and the periods corresponding to the I mode. We note that, for a given damping, the acceleration spectrum depends on the nature of the soil, figure 18. Eigenperiod, S, acceleration and G00, 40, 81, 21, 62, 02, 42, 81, 41, 21, 00, 80, 60, 40, 2.0, 000, 20, 050, 100, 20. Eigenperiod, S, acceleration in G1, 41, 21, 00, 80, 60, 40, 21, 80, 51, 01, 52, 02, 53, 000 cohesionless soils, great depth rock, steep soils 0,05 equals. Figure 18, average spectrum of a magnitude 6.5 earthquake at 8 km from the focus for various site conditions according to 17. 010110110-110210110110-010 frequency in pseudo acceleration in 2 ms spectre USA 1.0,020,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0,0Figure 20, USA 1 standards, according to 9. 4.2.6 Calculation of the dynamic characteristics of embankments. The calculation of the dynamic characteristics of the embankment such as peak acceleration and natural periods depends on the average distortion 9 experienced by the structure. This dependence results from the fact that the dynamic shear modulus and damping vary with the distortion, figures 10 and 11. The calculation procedure, which is summarized in the flowchart in figure 21, recommends the following steps. Figure 21, flowchart for calculation of embankment peak acceleration, natural periods, and equivalent cyclic distortion 19. 4.2.7 Calculation of induced permanent displacements. Knowing the value of the acceleration. At the crest of the embankment, using the chart in figure 7, the value of the maximum acceleration coefficient of the unstable part of the embankment is determined. Embankment. The ratio is calculated. If this ratio is strictly less than 1, the induced permanent displacements are given by the charts in figure 8. If this ratio is greater than 1, the embankment is stable and the calculation of the induced permanent displacements is not applicable. For application. 4.1 Maximum acceleration at the embankment crest. Consider a rock-fill dam of 180 m height resting on bedrock. The geometric characteristics of this dam are shown in figure 22. Laboratory tests show that the maximum shear modulus of the dam material is 600 Mpa, its cohesion is 0 and its angle of friction at failure is 400. The tests carried out in situ reveal that the shear modulus of the material in place is 216 Mpa and its density is the variations of the curves 2T/M3 and damping. And damping, percent, as a function of cyclic distortion obtained from the cyclic triaxial tests are equal to the average variations of the curves given by 17 and are illustrated in figures 10, and 11. The magnitude of the design earthquake is 7,5 on the Richter scale and its maximum acceleration at the base of the structure is equal to 0,25 g. The elastic response of the dam is obtained by multiplying the accelerogram spectrum in figure 16, by an amplification coefficient of 1,6. We evaluate the permanent displacements induced by the design earthquake for the plane failure surfaces given in figure 22, all of which pass through point I such that IB equals 11,5 m. We draw your attention to the fact that these flat surfaces are not critical failure surfaces for which the safety coefficient and minimum. Figure 22, rock-fill dam and slip following flat surfaces. The values of the shear modulus G equals 216 Mpa and the density equals 2T/M3 allow us to calculate the natural periods of the different modes of vibration of the dam which are given in Table 1. The application of the flowchart in figure 21 requires the calculation of the ratio equals 0.36 which allows us to use the curve in figure 10 to find the value of cyclic equals 0,065%. Moving to figure 11, we find a damping coefficient equals 10%. The values of the spectral acceleration associated with the different modes are determined using the curve f t dot. At the figure 16, for which equals 10% equals 1,6 asterisk f t equals 10%. 77. Where is the eigenperiod associated with mode I dot using formula 60 and 61, the peak acceleration of the barrage is found to be equals 0,62. And the equivalent distortion obtained equals 0,060% is very little different from its initial value, 0.065%. Using the charts of 20, average values, or the relations proposed by 19 we obtain the values of the induced permanent displacements D at different rupture lines which are given in Table 2 and Figure 23. Figure 23, permanent displacement induced by the magnitude 7.5 earthquake. From these results, we can see that for flat fracture surfaces, the earthquake-induced permanent displacements decrease as the ratio, increases. Furthermore, we see that the largest displacement obtained is 37 cm when, equals 0.25. 5 Conclusions. We have just shown that the simplified dynamic methods in general and in particular that of 20 allow engineers to Take into account the effects of earthquakes on embankments or slopes. Calculate the permanent displacements induced along a failure surface in order to verify the second criterion related to the concept of allowable displacements. However, the implementation of these methods requires that, the foundation soil and the materials constituting the embankment or slope studied must not only verify the non-liquefaction conditions, but also that the shear strength losses recorded at the level of the failure surface are 0 or less than 10% of its initial value.